Production models do not stay fixed in a stable world. The main issue here is what happens when the data changes after deployment and the model no longer matches reality. That grocery forecasting story shows a common trap. A model can earn trust during testing, then meet a different world in production. Once demand patterns drift, the same predictions that looked accurate at first start causing waste, lost sales, and expensive operational fixes. The important part is not just that the numbers got worse. The business now has to choose between paying for a model update, switching vendors, or building internal ownership, and all of those options cost time and money. A deployed model behaves more like a living system than a finished product. It needs ongoing checks so problems are caught early before bad predictions spread into real decisions and become harder to undo. The central theme is data distribution shift. The input data in production no longer looks like the data used for training. That shift is the starting point for understanding model decay, and it leads naturally into monitoring and then updating the model to adapt. ML system failures start with a simple question. Which expectation broke, and was it the software behavior or the model behavior? That distinction matters because the fix depends on the kind of failure. A failure means the system no longer meets what we expect from it. In traditional software, that expectation is usually operational. The service responds, stays within latency limits, and handles traffic at the right speed. For ML systems, the bar is higher. The system has to run correctly, but the model output also has to be good enough on the task itself, like producing a faithful translation within the required time. If the system never returns a translation, the operational promise is broken immediately. That counts as a failure even before we ask whether the translation quality would have been good. A single bad translation may still fall within the allowed error rate, so it is not enough by itself to call the system a failure. But if wrong outputs keep happening across many inputs, the performance expectation has been violated. Operational problems usually leave a trace, like a timeout or a crash, so they're easier to detect. Model quality problems are harder because they can look normal on the surface, and without labels or monitoring, poor predictions can slip through unnoticed. That is why the investigation has to separate software issues from ML-specific issues. Once that split is clear, it becomes much easier to trace why something worked in development but broke in production. Failures in ML systems are often ordinary software failures first. The important point is that many production problems come from the same causes that break any large codebase or service. That means the root cause is not the model itself. It's the surrounding software, infrastructure, and operations that keep the model running. A common example is a dependency breaking underneath you. If your service relies on a package or another codebase and that piece stops working, your own system can fail even when your model logic is unchanged. Third-party dependencies are especially risky because you do not control their maintenance. If the maintainer disappears or changes the interface, the breakage can arrive suddenly and affect everything built on top of it. Another frequent source of trouble is deployment. The code may be fine, but the wrong version gets shipped or the runtime environment does not match what the system expects. That can mean an older binary goes out instead of the current one, or permissions prevent the system from reading and writing the files it needs. Those are operational mistakes, and they can stop a model from serving correctly. Hardware is another basic failure point. The CPUs or GPUs that run the system may overheat, degrade, or otherwise stop behaving reliably. When a machine underneath the software becomes unstable, the software cannot compensate for that. Even a well-built model pipeline depends on healthy hardware to keep running. A service can also fail because something it depends on is temporarily unavailable. If one server or hosted component goes down, the rest of the system may have no way to keep working. This is why reliability has to be considered end-to-end. A single external service, network link, or hosted machine can become the bottleneck that takes the whole system offline. That pattern shows up in real systems too. At Google, a review of many broken ML pipelines found that most failures came from distributed systems mistakes or data pipeline mistakes, not from the models themselves. So these failures are handled with software engineering discipline, testing, deployment control, permissions, orchestration, and robust infrastructure. For ML engineering, that means a lot of the work is standard engineering rather than model training. As the tooling improves and production practices become more standardized, these ordinary software problems should become less dominant. Then the failures that remain will be more about the model, the data, and the ML behavior itself. ML systems fail in ways that ordinary software often does not, especially when data, deployment, and user behavior change around the model. The important part is that these failures can look small in development and become serious only after deployment. These failures come from the model's dependence on data and on the world around it. A bad training set, mismatched pipelines, drifting data, rare inputs, or self-reinforcing feedback can all break a model even when the code itself is correct. The focus here is on problems that appear after deployment, because that is where ML systems start meeting real users and real change. Even if they are less common than other failures, they matter more because they are harder to notice and can stop a model from being usable at all. A model only works well when the data it sees later behaves enough like the data it learned from. The first failure mode comes from that assumption breaking in production. Training means learning patterns from one finite sample, and evaluation tries to estimate how those patterns will hold on new data. If test data is a good stand-in for future data, performance there gives a reasonable picture of generalization. That classical assumption says the future will resemble the past closely enough for the model to keep working. When that stops being true, the model can lose accuracy even though nothing about the model code has changed. In practice, that assumption often fails because the real world is bigger, messier, and constantly sampled with bias. Even small differences, like a different emoji encoding, can create train-serving skew. The model looks strong during development and then disappoints in production. The other issue is that the world itself changes. Search intent, customer behavior, and language all move over time. So a model that was accurate at launch can slowly become stale unless performance is monitored continuously. Shifts do not require an unusual event. They happen in many ordinary ways. A product launch, a competitor's pricing change, cultural drift, or even seasonal demand can move the data enough to affect predictions. Monitoring can be misleading because a change in the dashboard may come from your own system rather than the outside world. Broken feature extraction, wrong model versions, missing values, or interface changes can all imitate a real distribution shift. This failure mode is common enough that it needs careful study on its own. The main idea to keep in mind is that production data can drift for real reasons, or it can appear to drift because of mistakes inside the system. The next problem is not about the whole distribution changing, but about rare inputs that trigger very bad behavior. In ML, a few extreme cases can be enough to block deployment entirely. A model can look excellent on average and still be unacceptable if the rare failures are disastrous. For self-driving car, a tiny error rate is not tiny at all if one mistake can cause injury or death. That is why edge cases matter so much in safety-critical systems. A model may work for most users, but if the failures are dangerous enough, the system is not ready for use. An edge case is usually a sample from the same general distribution, but one the model handles very badly. If those failures start showing up more often, that can also be a sign that the distribution itself has changed. The danger is not limited to autonomous vehicles or medical systems. A chatbot that produces racist or sexist responses a few times could be enough to make the whole product unusable because the reputation cost is too high. Outliers and edge cases are related, but they are not the same thing. The distinction matters because one describes unusual data, while the other describes poor model behavior. Different fields use these terms differently, and ML is still working out a stable definition because these systems are new in production. For that reason, it helps to be precise about whether you mean the data point itself or the model's response to it. An outlier is a sample that looks very different from the rest. It becomes an edge case only when the model performs badly on it, and not every unusual sample causes a failure if the model handles it well. During training, unusual points can pull the decision boundary in the wrong direction, so removing them can sometimes help the model learn a cleaner pattern. At inference time, though, you usually cannot remove the query, so the better goal is to build a model that stays reliable even when the input is strange. Focus on the difference between the two boundaries. The left side is shaped by the normal examples, while the right side bends because of the single outlier, which shows how one unusual point can distort the learned rule. That comparison makes the training problem concrete. A single outlier can shift the boundary far enough to hurt accuracy on ordinary cases. It is a reminder that robustness during learning and robustness during serving are related, but not identical. The last failure mode comes from a model influencing the very data it later learns from. Once predictions change user behavior, the system can start reinforcing its own bias. A normal feedback loop measures how long it takes for a prediction to get a response, and that response can become a label for the next model. The trouble starts when the prediction itself changes what users do, so the feedback is no longer neutral. That creates a self-reinforcing system. The model's output affects user action. User action becomes training data, and the training data pushes the next model in the same direction. This is common in recommender systems and ads, where exposure can strongly affect what gets clicked. A slight advantage at the top of a recommendation list can create much more engagement, and that extra engagement makes the item look even better to the next model. Over time, the system can freeze into a narrow set of popular items, which is why the same phenomenon is also called exposure bias or filter bubbles. The same pattern appears in hiring or screening systems when a model learns a proxy that is already tied to opportunity. If the model keeps recommending one feature and the organization keeps rewarding those recommendations, the bias becomes stronger with each round. Left alone, these loops can make a system worse at its task and worse at fairness. The danger is not only lower accuracy, but also the way the system can keep amplifying patterns that should never have been reinforced. Detecting this problem is difficult because the loop only exists once users are actually interacting with the system. Offline testing helps, but the strongest evidence often appears only after deployment. Offline, you do not yet have real users changing their behavior in response to predictions. That means the loop is partly hidden until the system is live, which makes proactive measurement especially important. For recommender systems, one clue is whether the outputs become too concentrated on a small set of popular items. Diversity metrics, such as aggregate diversity and coverage of long-tail items, help reveal when the system is overfavoring what is already popular. Another useful check is to compare hit rate across popularity groups. If the model is much better at recommending popular items than rare ones, the pattern points toward popularity bias and a possible feedback loop. Once the loop is visible, the goal is to reduce the self-reinforcement without destroying usefulness. Two practical ideas are randomization and positional features. Both methods try to separate true item quality from the behavior caused by exposure. One changes what users see, and the other helps the model account for where an item was shown. Randomization gives less popular items a chance to earn feedback that is not dominated by their rank position. Systems like TikTok use this idea by giving new videos an initial pool of traffic, so their quality can be measured before wider distribution. A pure random strategy is usually too costly because people stop trusting the recommendations. A better approach is controlled exploration, where the system gathers unbiased signals without making the product feel chaotic. Position matters because users pay more attention to items near the top. If the top item gets more clicks, the model must decide whether that happened because it was genuinely better or because it simply had the best placement. One way to handle that bias is to feed the position into the model as a feature. Then the model can learn that being shown first affects the chance of a click, rather than treating every click as if it reflected quality alone. The simple training trick is to record whether an item appeared first, so the model can learn the effect of top placement. That gives the learner a way to separate item quality from exposure effects. The table makes the feature engineering idea concrete. The same song can have different click outcomes depending on whether it was shown first, which is exactly the kind of information the model needs to see during training. At prediction time, the goal changes. You want the model to judge interest without assuming a particular placement. After that, you can choose the display order separately, using the scores the model produces for each candidate item. The naive feature trick is often not enough. So a cleaner design is to split the problem into two stages. One model estimates whether the user will even see and consider the item, and a second model estimates the click once exposure has been accounted for. Changes in the data stream can break a model even when the model itself never changes. The important idea here is that training and deployment often happen in different distributions, and that mismatch is a major source of falling accuracy. A model learns patterns from one distribution and then gets used in another. When the source distribution and target distribution diverge, the model's assumptions start to drift away from reality, and predictions become less reliable over time. This problem is not new just because machine learning is popular now. Researchers have studied dataset shift for a long time, and that older work gives a useful vocabulary for thinking about why models fail when the world changes around them. Data shift is not one single thing. The useful distinction here is between covariate shift, label shift, and concept drift, because each one changes a different part of the data generating process. These subtypes matter most when the goal is to build detection or adaptation methods, since the right method depends on what changed. In practice, people usually care more about handling the shift than naming it perfectly. The starting point is to treat the training data as samples from a joint distribution over inputs and outputs. Once that joint distribution is written down, it can be factored in two different ways, and those two factorizations are what make the shift definitions precise. The first factorization separates the output given the input from the input distribution itself. One way to read this is predict the label from the input, then weight that by how often the input occurs. That split is the basis for covariate shift and concept drift. The second factorization instead starts from the label and conditions the input on it. This version is useful when the class balance changes. It separates how often each label occurs from the feature patterns associated with that label. Those three terms are the moving parts. If the input density changes, we call that covariate shift. If the label density changes, that points to label shift. And if the mapping from input to output changes, that is concept drift. Covariate shift means the input side of the problem changes while the conditional relationship from input to output stays stable. The feature distribution moves, but the rule connecting features to labels does not. That distinction matters because the model may face a different mix of inputs, even though the underlying labeling rule is unchanged. Label shift means the class proportions change, while the feature pattern within each class stays the same. The population of labels changes, but each label still generates the same kind of inputs. That is why this shift is often tied to changes in class prevalence rather than changes in the feature-to-label rule. Concept drift is a change in the relationship between input and output itself. The features are distributed as before, but the meaning of those features for prediction has changed. That is why the same input can lead to a different expected output over time. The formulas are dense at first, so concrete cases help. Once the examples are on the table, the difference between changing inputs, changing labels, and changing the rule becomes much easier to see. Covariate shift is the most widely studied form because it appears whenever the input population changes without changing the labeling rule. In statistics, a covariate is a variable that influences the result even if it is not the main variable of interest. In a housing example, square footage is a covariate because it affects price, and in supervised learning, the features play that role while the label is what we want to predict. The input distribution moves, but the conditional model stays valid. So the challenge is not that the rule changed. It is that the model now sees a different mix of inputs than it saw during training. In the breast cancer example, suppose the test population has fewer people over 40 than the training population. The age distribution has shifted, yet for a fixed age group, the probability of cancer is assumed to stay the same. This often happens when the training data is collected from a source that overrepresents certain groups. A clinic dataset, for example, may contain many more older patients simply because older people are more likely to be tested. Artificial changes to the training set can do the same thing. If rare classes are oversampled, the feature distribution in training no longer matches the real-world feature distribution. Active learning also changes the picture because the model is trained on samples chosen for usefulness rather than random chance. That selection step makes the training inputs differ from the real-world inputs, so covariate shift appears as a side effect. In production, the same pattern shows up when the environment or user base changes. If marketing attracts a wealthier audience, the income distribution shifts, but the conversion rule for a given income level may still be the same. When the new input distribution is known in advance, importance weighting can help. The idea is to estimate how the real-world input density differs from the training density, then reweight training examples so the model behaves as if it had seen the target distribution. The difficult part is that future shifts are usually not known ahead of time. Research tries to learn representations that stay invariant across distributions, but those methods are not yet the default in industry practice. Label shift flips the focus to the output side of the distribution. The class balance changes, but the relationship between class and features stays stable. This means the prior probabilities move, while each class still produces the same kind of inputs. You can think of it as a change in how common each label is, not a change in what the labels look like. These two shifts are closely connected because changing the input mix often changes the label mix too. In the breast cancer example, fewer older patients in the test set means fewer positive labels overall, yet the feature distribution within the positive class can remain the same. A preventive drug changes the cancer rate across ages, so the output distribution shifts. Even so, among people who already have cancer, the age pattern can stay the same, which keeps the class conditional input distribution unchanged. Because the two shifts are related, many detection and adaptation methods look similar. The main difference is whether the correction is aimed at the input distribution or the label distribution. Concept drift is different from the other two because the prediction rule itself changes over time. The features may look the same, yet the same features now imply a different output. A house with the same characteristics can have a different price after the market changes, so the conditional relationship has moved even though the input distribution has not. This kind of drift often repeats in cycles, which is why separate models are sometimes used for weekdays and weekends or for holiday and non-holiday periods. The underlying input space may stay similar, but the mapping from input to output changes with time or context. Data can change in ways that hurt a model, even when the research literature does not give those changes a neat label. The important idea is that real systems face shifts in the data, and those shifts can quietly reduce performance. A model is only as reliable as the data it expects to see. When the world changes around it, the model can start making worse predictions even if the code itself never changes. Feature change means the input side of the problem has shifted. A column can disappear, a new one can appear, or the values can move into a new range. And even something as simple as changing age from years to months can break the model's assumptions. A pipeline bug that turned a feature into nans is another version of the same problem, because the model is suddenly receiving values it was never trained to handle. Label schema change affects the output side of the task. The label set itself changes, so the meaning or structure of the targets changes too. That is different from ordinary label shift, where only the class frequencies move while the relationship between X and Y stays the same. For regression, the schema can change when the valid numeric range changes. A credit score model trained on one scoring system may suddenly face a new scoring scale, and that changes what the prediction target even means. For classification, the label schema changes when classes are added, removed, or split into finer categories. A sentiment model that used 3 labels may need a 4th label, and that can force relabeling, a change in model structure, and retraining from scratch, especially when the class set is large. These shifts do not arrive one at a time in a clean package. A single model can face several kinds of drift together, which is why diagnosing and fixing the problem becomes much harder. Detecting a shift matters only when it starts affecting model behavior. The goal here is to watch for changes in the data, the labels, and the model's performance, so you can tell when a change is just noise and when it needs action. A drop in accuracy, recall, F1 or AUC, is often the first sign that the production data no longer matches what the model learned from. A rise or a sudden wobble can matter too, because unusual movement usually means something in the data pipeline or user population has changed. Those metrics depend on ground truth, and that is the hard part in production. Training gives you labels immediately, but serving often does not. So any monitoring system that gets labels within a reasonable delay has a major advantage for spotting trouble early. When labels are not available, the next move is to watch the distributions directly. Input features are usually the easiest to inspect, while label and conditional shifts are more informative but also harder because they depend on knowing why. Research has methods for estimating label shift without labels, but many production systems focus on feature drift because it is the most practical signal to monitor. The main idea is simple. If the inputs start changing, the model may be operating in a new regime even before labels arrive. Statistical drift detection starts with comparing two samples and asking whether they look like they came from the same distribution. The simplest tools use summary numbers. The stronger tools use formal tests. A common first check is to compare means, medians, variances, quantiles, and similar summaries between training and serving data. That can reveal a shift quickly, but matching summary statistics does not prove the distributions are the same, so it is only a rough screen. A two-sample test goes beyond summaries and asks whether the observed difference is likely to be real rather than random sampling noise. If yesterday's data and today's data are statistically different, that is evidence that the underlying distribution has changed. A tiny difference can become significant if you collect enough data, so the size of the sample matters. A useful rule of thumb is that differences found with small samples are more likely to deserve attention than differences that only show up after huge amounts of data. The KS test is a classic non-parametric two-sample test, which makes it flexible for one-dimensional numeric data like predictions or labels. Its limitation is that it does not scale well to high-dimensional feature spaces, and in practice it can also be slow and noisy. More advanced methods, such as least squares density difference and MMD, handle richer data types, especially in multivariate settings. They are widely discussed in research, and libraries like Alibi Detect collect many of them in one place for experimentation and deployment. Because high-dimensional data makes these tests harder to use well, dimensionality reduction is often a smart pre-processing step. It can make the comparison more stable and easier to interpret before you run the actual test. The main thing to notice in a library like this is the range of detectors it offers, from simple statistical checks to more advanced methods. That variety matters because no single detector is best for every kind of drift problem. The figure groups several detection approaches together, which makes the trade-off visible at a glance. Some are easier to deploy, while others are more expressive but heavier to use. That contrast is useful when choosing a method for production monitoring. Detecting drift over time depends on the time window you choose. A short window reacts quickly, but a longer window can separate true change from ordinary seasonal patterns. Not every shift behaves the same way. A sudden change is easy to spot, while a slow drift can blend into normal variation, and temporal changes often interact with where the data comes from, such as device type or user group. The window you choose controls what pattern becomes visible. If the data has a weekly rhythm, a short window may misread normal cycle changes as drift, while a longer window can absorb that rhythm and make the underlying pattern clearer. The key comparison in the figure is between a shorter source window and a longer one. With a shorter window, a new day can look unusual. With a longer window, that same day may fit the broader seasonal pattern. The point of the figure is that drift is not an absolute label. It depends on the baseline you choose, which is why timescale selection is part of the monitoring design itself. Running statistics can be computed in two different ways. Sliding statistics isolate one window at a time, while cumulative statistics keep folding in older data, which can smooth away a real problem that happened recently. The important visual pattern is the difference between the short window and the all-time average. A temporary drop may disappear inside the cumulative line, even though the sliding view catches it clearly. The figure highlights why cumulative metrics can be misleading for monitoring. A problem that lasts only a few hours may matter a lot operationally, but it can be diluted away if the history is too long. Working in time makes drift detection more complicated because seasonality has to be separated from genuine change. That is where time series decomposition and related analysis methods become useful, especially when demand or traffic has a repeating pattern. Many production systems use the training distribution as the baseline and compare it with hourly or daily production data. Short windows react quickly, but they also make ordinary fluctuations more likely to look like a shift. A practical compromise is to compute fine-grained statistics first and then merge them into broader aggregates. That gives you both speed and flexibility because the same hourly summaries can also support daily monitoring. More advanced monitoring systems try to pinpoint the first window where the behavior changed. That kind of root cause analysis helps narrow the investigation because you can focus on the exact period where the drift started instead of scanning the entire history. Data shifts matter because a model that worked well at launch can become unreliable after the environment changes. The main question is how to keep production systems useful when the data they see no longer matches training data. Teams that are just starting with machine learning often focus first on getting a model into production. Only later do they discover that the model's mistakes have grown large enough that the system causes harm instead of value, and at that point, they need to adapt the model or replace the approach. A common response is scheduled retraining, monthly, weekly, or even daily. The hard part is choosing that cadence well, because too much retraining wastes effort and too little lets the model drift into poor performance. Many companies still choose that frequency by judgment rather than measured evidence. One strategy is to make the training data so large and diverse that the learned distribution is broad enough to cover most future inputs. That approach reduces surprise in production, but it depends on being able to collect enough representative data in the first place. A second strategy tries to adapt a model to the new distribution without labeling fresh target data. That line of work includes unsupervised domain adaptation, but it is still less mature and much less common in industry than retraining with labels. The most common industrial approach is to retrain with labeled data from the new distribution. That retraining can mean starting over from scratch or continuing from an existing model. And when training continues from the current weights, people usually call it fine-tuning. Two decisions matter most here. First, whether to restart training completely or continue from the last checkpoint. Second, how much recent data to include, since the best window might be the last day, the last week, or the point where drift began, and the right answer usually comes from experiments. The term retraining is being used broadly here to cover both restarting a model and continuing an existing one. That matters because the same word can hide very different engineering choices, and those choices affect cost, speed, and model behavior. Data shift has close neighbors in the literature. If you think of a distribution as a domain, then adapting across shifts looks very much like domain adaptation, because the core problem is learning to handle a different data environment. The same idea can also be framed as transfer learning when the task is to reuse a model trained on one joint distribution for another. The difference is that transfer learning usually reuses a starting model, while adapting to a new distribution may still require full retraining. Good systems do not just react to drift after it happens. They can be designed to withstand it better. A feature may be highly predictive, but change quickly. So in practice, you often trade a little accuracy for a feature that stays useful longer and does not force constant retraining. System design can also make adaptation easier by splitting one global problem into parts that drift at different rates. If rural and urban markets change differently, separate models let each one update only when its own data actually demands it, instead of dragging both along at the pace of the fastest changing market. One more caution matters before leaving this topic. Lower production performance does not always mean the data changed. Human errors can create failures too. And in those cases, the first job is to find and fix the operational mistake, because identifying the cause can be harder than spotting the drop in metrics. Monitoring and observability are the tools that tell you when an ML system is healthy and when it needs attention. That matters because a model can be accurate in theory and still fail badly in production. Once ML systems started breaking in real deployments, companies had to treat them like any other production service. The focus shifts from model quality alone to whether the system is behaving safely and reliably under real traffic. Monitoring tells you that something looks wrong by tracking numbers and logs over time. Observability gives you enough internal visibility to investigate why it went wrong, and instrumentation is the work of adding timers, counters, and logs so that visibility exists in the first place. The first layer of monitoring is operational health, because an ML service is still software running on networks and machines. Latency, throughput, error rates, and resource usage tell you whether requests are flowing and whether the infrastructure can keep up. If the service is down, the model quality does not matter. Availability turns into a measurable target through uptime, which is the fraction of time the service meets the agreed performance level. SLOs and SLAs define the line between up and down, often using latency thresholds such as a median under 200 milliseconds and a 99th percentile under 2 seconds. Those percentages become very concrete once you convert them into downtime. 4 nines leaves only a few minutes of outage in a month, and 5 nines leaves only seconds. So small changes in the percentage represent a very strict reliability promise. For ML systems, health goes beyond whether the service responds. If the model stays online, but the predictions drift, become biased, or lose accuracy, users still experience failure. So model-specific metrics have to be monitored alongside the operational ones. ML systems need metrics that tell you not just whether software is running, but whether the model is still behaving well. The next few artifacts give you different views into where a problem may be coming from. Those 4 artifacts sit at different points in the pipeline, so they tell you different things. Deeper artifacts are closer to the source of truth, but they also pass through more transformations, which makes debugging harder and monitoring more useful at the same time. The key idea in the figure is the trade-off between being close to the final metric and being easy to interpret. As an artifact moves through more processing steps, it becomes more structured and easier to monitor, but any change also has more possible causes upstream. That trade-off is what the figure is trying to make visible. The farther along the pipeline you are, the more informative the signal becomes, but the harder it is to trace a change back to one exact step. Accuracy-related metrics are the closest thing to the model's real scorecard. They matter because they tell you whether users are seeing better or worse predictions, not just whether the system is mechanically producing outputs. When users click, buy, upvote, or otherwise react, that feedback can become a label or a clue about one. Those signals are the most direct way to measure whether performance has started to slip. A single metric can miss an important failure mode. In a recommender, people may still click the item, but if they stop watching it or finish it less often, the recommendation quality is probably getting worse even though the click rate looks stable. Sometimes the system has to be designed to ask for feedback explicitly. Upvotes and downvotes do two jobs at once. They help judge quality now, and they create hard examples that human labelers can use to train the next model. The important part in the figure is the feedback loop from the user back into the training process. A vote is not just a rating. It is also a signal that can steer which samples deserve expert review. That pattern turns production behavior into training data. When downvotes rise, they can point to a quality problem and also help choose the next examples to label. Predictions are often the first artifact worth watching because they are cheap to collect and easy to summarize. Even before labels arrive, the shape of the predictions can reveal that something has changed. A regression model gives you a number, and a classifier gives you a category. Because those outputs are simple, you can plot them, compute summary statistics, and spot odd patterns without much effort. If the model itself has not changed, then a new prediction distribution often means the input distribution has changed underneath it. That makes predictions a useful proxy for catching drift early. Some failures are visible long before labels arrive. A model that suddenly predicts one class over and over can be caught in minutes, while accuracy metrics may not move until much later. Features are where many monitoring systems spend most of their effort. They sit close to the model input, so they're useful for debugging, data quality checks, and drift detection. Feature monitoring starts with schema validation. Are the values in the shape and range you expect? That means checking things like numeric ranges, formats, allowed categories, and relationships between columns before you even talk about distribution shift. The first check is often very simple. Does the feature stay within the values you expect? Once that basic guardrail is in place, deeper checks become much more meaningful. Range checks catch obvious corruption quickly. If a value jumps far outside the usual bounds, the data may be malformed, missing, or transformed incorrectly. Some features are text, IDs, or codes, so structure matters as much as numeric range. For those, the question is often whether the value matches the expected pattern. A regular expression check is useful when a feature has a fixed format, like an email, postal code, or product code. It is a fast way to catch strings that do not belong in that column. Some columns should only contain a small set of allowed values. That kind of constraint is easy to check and very good at catching unexpected labels or typos. Category checks protect you from new or invalid classes showing up in production. If a value falls outside the approved set, the issue is usually in the data pipeline or in upstream business logic. Relationships between features can matter too. A single column may look fine on its own, but it can still violate an expected rule when compared with another column. Cross-feature rules catch impossible combinations. If one value should always exceed another, breaking that rule often points to a bug in pre-processing or in the way the columns were assembled. Because features are usually stored in tables, these checks are often treated like unit tests for data. Tools such as Great Expectations and Deco make it easier to express those checks and run them repeatedly. The figure highlights the kinds of tests that are easy to automate: ranges, type checks, set membership, and relationships between fields. Those are the building blocks of a practical validation suite. Those built-ins matter because they let you turn data expectations into executable checks. Once the checks are explicit, they can run the same way every time new data arrives. Validation catches broken rules, but it does not catch subtler drift. For that, two sample tests compare current data with a reference distribution, though the test gets harder when the feature set is high-dimensional. Feature monitoring sounds straightforward, but it brings several practical problems. Scale, cost, usefulness, and alert quality all become part of the design choice. At production scale, the number of track columns explodes quickly. Even before computing anything fancy, just keeping track of all those features can become a large operational burden. Repeatedly computing metrics across all those columns costs compute and memory, and it can add latency to the system itself. Monitoring should help you detect problems, not become one more source of slowdown. Feature changes are useful clues, but they do not always tell you whether the model is truly worse. A drifted feature may be harmless, so the signal is often stronger for debugging than for judging final model quality. That is where alert fatigue comes from. If every small shift triggers an alert, the team starts ignoring the alerts. So the real job is deciding which shifts are worth attention and which ones are normal noise. The harder part is that feature creation is rarely a single clean step. It can move through cleaning, standardization, and multiple systems, so a bad feature value may be caused anywhere along that path. Once a feature has been transformed several times, the source of a problem becomes ambiguous. The same bad value could come from a real change in the data or from a bug in one of the processing stages. Schemas are not fixed forever. When the definition of a feature changes, your monitoring needs to know which version it is comparing against, or the alert will be misleading. Without schema versioning, a valid new schema can look like a broken old one. That makes it important to tie each monitored feature back to the expectation it should actually follow. These issues do not make feature monitoring less valuable. They just mean the alerts should be designed with context, so the signals help you understand the system instead of overwhelming it. Raw inputs sit even earlier in the pipeline, so they can help separate source data problems from feature engineering problems. The difficulty is that raw data is often messy, distributed, and owned by a different team. Raw inputs can come in many formats from many sources, which makes them harder to standardize than model features. In many organizations, ML engineers do not even have direct access to that data, so monitoring it is often handled by the data platform team instead. That closes the loop on the main metric types. First, the general software signals, then the model-specific signals that track inputs, features, predictions, and outcomes. The next step is choosing the tools that let those signals run reliably in production. Monitoring needs more than raw measurements. It needs tools that help people find problems, understand them, and react in time. Logs, dashboards, and alerts are the user-facing parts of that toolbox. The usual three pillars are metrics, logs, and traces, but the boundaries between them can get blurry. A more practical view is to ask what helps the person operating the system. Logs for detail, dashboards for patterns, and alerts for action. Logs are the starting point for understanding runtime behavior. They capture events so that later you can reconstruct what happened inside a system. A log entry should capture anything that might matter later. Startup events, function calls, inputs, outputs, crashes, stack traces, and error codes. The goal is simple. If something changes or fails, there should be a record of it. The scale becomes the hard part very quickly. Once a system produces billions of events, the challenge is not collecting logs, but searching through them efficiently when an incident happens. A single service application usually makes ownership obvious, but distributed systems do not. Requests may pass through many containers, services, and routing layers. So the important question becomes where the failure happened, not just that it happened. Distributed tracing solves that search problem by tying related events together with a unique identifier. When every log line carries the same request ID, time, service name, function name, and user context, you can follow one path through the whole system. Once logs reach that scale, ad hoc handling stops working. That is why companies build and buy tools for storing, querying, and analyzing log streams instead of treating logs like ordinary text files. Machine learning is useful when manual inspection is no longer realistic. It can flag unusual behavior, and it can also assign severity labels so that routine events and critical failures are separated more quickly. Another useful model asks how a failure in one service may affect nearby services. That kind of dependency estimate is especially valuable during outages and attacks, when one bad component can trigger a wider chain reaction. Batch systems work well when throughput matters more than immediacy. They let you query large log collections with SQL or distributed frameworks, but the trade-off is that you only discover issues on the batch schedule. When the goal is to catch anomalies as they happen, logs have to be processed as a stream. Transport systems like Kafka or Kinesis move the events immediately, and streaming SQL engines can filter or search them without waiting for a batch job. Dashboards turn raw metrics into patterns the eye can understand. They help operators see relationships, trends, and surprises that are hard to spot in numbers alone. A table of numbers often hides the story, while a graph can reveal shape, trend, and correlation at a glance. That is why visual monitoring is such an important complement to logs. Dashboards are not just for engineers who know the internals of the system. Product managers and other stakeholders can use the same displays to understand whether the system is behaving in a way that supports the business. A graph can make variation visible without making it understandable. If the underlying question is distribution shift or model degradation, you still need statistical reasoning to tell whether the change matters. The important thing to read in these plots is the amount of fluctuation, not a precise answer hidden in the line itself. A wiggly curve can tell you that behavior is changing, but it cannot tell you by itself why the change happened or whether it is acceptable. This figure reinforces a common monitoring mistake: seeing motion and assuming understanding. The graph is a clue, not the diagnosis. A dashboard can become cluttered enough that nobody can tell which metric matters. Good monitoring often means reducing low-level measurements into a smaller set of signals that match the task at hand. Alerts connect detection to action. Once the system notices something suspicious, the next job is making sure the right person hears about it quickly and clearly. A useful alert is more than a bell that rings. It needs a rule for when to fire, a way to reach people, and enough context that the person receiving it can respond intelligently. The policy defines the condition itself. It says what threshold or pattern is serious enough to deserve attention. That condition is usually a metric limit, sometimes sustained for a period rather than crossed for a single moment. Requiring duration helps avoid noise from brief spikes that do not represent real trouble. The notification channel decides where the alert lands. Different channels reach different people, so the system has to send the message to the places where responders actually pay attention. A monitoring platform may display the alert, but that is not enough on its own. Responsible people often need email, chat, or paging so they can respond even when they are away from the dashboard. The alert message itself should explain what happened in plain operational language. Without that context, the person reading it has to waste time reconstructing the problem from scratch. Good alert text points to the model, the service, the time, and the likely cause. The more specific the message is, the faster someone can decide whether to investigate, mitigate, or escalate. These two lines give the reader the essential facts right away: what metric failed and where it came from. A template like this makes the alert searchable and helps the responder connect the message to the exact service and time window. A good alert should not stop at diagnosis. If the next step is a routine fix, the message should point to the runbook or give the mitigation steps so the responder can act immediately. Too many trivial alerts train people to ignore the system, and that is dangerous. The real goal is to reserve attention for the signals that truly need a human response. Observability is about understanding a system from the signals it produces. The important shift here is from simply detecting that something is wrong to inferring what is happening inside the system. Traditional monitoring watches the outside of a system and uses those external outputs as clues. That works for spotting a failure, but the clues may or may not be enough to identify the internal cause. That approach used to be enough when systems were small and teams controlled the whole code base. If something broke, you could change parts of the system, test them, and narrow down the fault directly. Today, the pieces are often spread across many services, and some of those services belong to other companies. When the internals are out of your control, the only reliable view comes from the outputs those components expose. That is the core idea borrowed from control theory. Enough output data can reveal how a complex system is behaving. The practical goal is better visibility into runtime behavior without needing to peek directly into every component. Telemetry is the name for the runtime data collected from a system. It is the raw material observability depends on, especially when the system is remote or spread across devices and cloud services. The word points to measurement at a distance. In practice, that means logs and metrics coming from services, applications, or devices you cannot inspect locally. This is a stronger claim than ordinary monitoring. It says the outputs should carry enough information to tell you not only what changed, but also what internal state the system was likely in. When the system is observable, the investigation happens through collected data rather than new deployments. Good instrumentation gives you enough runtime information to diagnose problems after they occur. Aggregated metrics tell you that performance changed, but finer-grained telemetry tells you where and for whom it changed. That makes it possible to ask targeted questions about subgroups, outliers, and even intermediate values flowing through the system. For machine learning systems, the model itself is only one part of the picture. Interpretability helps explain the model's decisions, while observability connects those decisions to the behavior of the full system around it. Monitoring tells you that a shift has happened, but it does not fix the shift on its own. The next step is a method that can respond to changes directly by updating the model as new conditions appear. Production failure is the main theme here. What breaks after deployment, why it breaks, and how to notice it early enough to respond well. That gap matters because the practical problems are real, but the research base is still thin. In this area, production has moved faster than the literature, so the field is still building its understanding from live systems rather than from mature theory. That distinction helps separate ordinary engineering breakdowns from failures tied to the model itself. Most incidents today still fall into the first category, but as the surrounding infrastructure improves, the ML-specific cases become more important to understand. These three causes cover a lot of real deployment trouble. The first two come from the data a model sees, while feedback loops come from the system design, where the model's own output changes the inputs it later receives. Distribution shift is one of the most active areas because the world rarely stays the same after training. The names are not always used consistently across papers, and many methods assume labels or future knowledge that you usually do not have in production, which makes the practical problem much harder. Monitoring turns drift detection into an operational habit. The best lessons here come from DevOps. Watch the live system continuously, because you cannot rely on users or bad outcomes alone to tell you when something has changed. Operational metrics tell you whether the software is healthy. Latency, throughput, CPU use, and similar signals. ML-specific metrics add the model view, so you can watch predictions, features, raw inputs, and any accuracy-related measures that are available. A dashboard can make a system look visible without making it understandable. The difficult part is deciding whether a graph shows real drift, a pipeline error, or ordinary variation, and that often needs statistical judgment rather than just more charts. Finding that performance has dropped is only the first step. The next question is how to change the system safely as the environment changes, and that sets up the transition into the next chapter. Inventory systems are a good example of how a model can end up shaping the data it later trains on or predicts from. That creates a loop, so the system is no longer just observing the world. It is partially creating the world it measures. That is one reason companies hesitate with startup software and often prefer open source. If the original creators stop maintaining the product, access to the codebase gives you a way to keep the system alive yourself. Not every failure comes from code or models. Physical systems can break too, so it helps to remember that deployed ML lives inside real hardware, with all the ordinary fragility that comes with it. A server crash may look like a normal infrastructure issue, but heavy ML workloads can raise the odds of that crash. That is why the boundary between ML and non-ML failure is useful, but never completely clean. Autonomous driving pushes the idea of edge cases into the open because rare situations matter a lot when the system is operating in public. A small number of unusual events can dominate the risk profile, so long-tail behavior becomes central. That phrase captures why researchers care so much about models that hold up outside the training set. A model that works only in the lab is not enough. The hard part is making it behave well when the environment is new or messy. This book points to a deeper body of work on non-stationary environments. The main idea is that when inputs change, You may need methods that explicitly adapt to those changing input distributions. Many modern systems run into a simple constraint. They need more data than is easy or economical to collect. That is why the pace of improvement is often tied not only to better models, but also to whether the data supply can keep up. That estimate is a useful reminder that drift is not always a mysterious natural phenomenon. Very often, the cause is operational, a bad pipeline change, a mislabeled field, or some other human mistake upstream. That comparison only makes sense once you choose a specific rate and a specific baseline. The point is not that the system is perfect. It is that raw numbers need context before they mean anything useful. That literature shows how hard it is to cover the full long tail of driving situations. Simulations, location data, and careful scenario analysis all help, but the core problem remains that rare situations are exactly where the system can surprise you. That term just names legal discovery when the evidence lives in electronic form. It matters here as another example of a domain where machine learning must work with messy, real-world data and changing input conditions. Recommender systems can feed their own outputs back into future data, which makes them especially vulnerable to self-reinforcing loops. Once popularity starts to dominate, the system can keep amplifying the same items and narrowing what users see. That connection matters because the data you observe is often shaped by what survived the process before it reached you. In other words, the sample you see may already be filtered by earlier system decisions. Recommendation systems can push a small set of popular items even harder, which changes sales diversity and user exposure. Once that happens, the system is no longer just reflecting demand. It is actively steering it. That work is a reminder that ranking metrics alone do not capture how a recommender behaves in practice. Testing should also ask what the system does to users, not just how well it scores against a benchmark. That example points to the same loop. A recommender learns from engagement, then uses that engagement to shape the next set of recommendations. When the loop is tight, the system can become very effective at holding attention, but also very sensitive to its own incentives. That line shows there are algorithmic ways to counteract popularity concentration. Instead of only optimizing for a single item score, you could design ranking methods that preserve more variety across the whole set of recommendations. That idea borrows from causal thinking. If recommendations change user behavior, then evaluation should account for the effect of the recommendation itself, not just the observed clicks afterward. Incremental learning matters because deployed data is rarely clean. A system often has to keep updating while the incoming stream contains errors, missing values, or other noise that would be hard to avoid in practice. That remark points to a boundary in the research itself. There are shift patterns we can define mathematically, but not every mathematically neat case has a practical method attached to it yet. Those areas study how to move knowledge from one data setting to another. When the future data differs from the training data, adaptation is one of the main ideas people reach for. A medical example helps because the distribution problem is easy to see when the population changes. Models trained on one group may not behave the same way on another, so the shift is not abstract at all. That method tries to adjust for changes in the input distribution. It is one of the classic tools for covariate shift, where the features move even if the underlying label relationship is not assumed to change. The environment is the key idea there. The data generating process is not fixed. When that happens, a model needs methods designed for change, not just a one-time training fit. Importance weighting tries to make the training data behave more like the target data by reweighting examples. That approach can help, but it also depends on assumptions that are not always easy to satisfy in real deployments. The goal there is to learn features that stay useful across environments. If the representation captures what is stable rather than what is accidental, the model has a better chance of transferring to a new domain. That is the hardest version of shift because the model faces changes on both sides of the prediction problem. When both the inputs and the mapping to labels move, many simpler adaptation tricks stop being enough. That detail matters because the output layer of a classifier is tied to the class set. If the number of classes changes, the parameter shape changes too, and that affects how the whole model could be reused or adapted. That reduces one of the practical obstacles, since labels are often the expensive part. But most production systems still rely on supervised learning, so label availability remains a major constraint in practice. That criticism is part of a broader point. Not all monitoring tools handle distribution change equally well. A detection method can look convenient on paper and still be weak in practice if it produces unclear or misleading signals. Once you start comparing distributions, you are really doing statistical reasoning, even if the tool hides that fact. That is why the quality of the interpretation matters as much as the graph itself. That warning is useful because no single test solves all drift problems. A test may work well in one setting and fail badly in another, especially when the data are high-dimensional or the assumptions are shaky. Validation catches issues before they become production incidents. In practice, that means checking inputs, schemas, ranges, and other constraints so that bad data does not silently flow into training or inference. That approach compares densities rather than relying only on labels. It is valuable because some shift detection methods can work even when direct ground truth is missing, which is often the case in live systems. That study is a reminder to be cautious about optimistic claims. A method may look elegant in theory, but real data can expose weaknesses very quickly, especially when the shift is subtle or the signals are noisy. Early warning systems matter because they give you time to react before the model degrades too far. The basic idea is to detect unusual patterns as soon as possible, even if the signal is imperfect. That topic keeps evolving because time series systems bring special constraints: speed, volume, and changing patterns over time. Real-time detection has to work under those practical limits, not just in a clean offline setting. A fine-time granularity can matter when the system changes quickly. The shorter the window, the faster you can react, but the harder it becomes to keep the signal stable and meaningful. Practical monitoring often improves through small adjustments shared by other engineers. Those details do not sound glamorous, but they're the sort of thing that makes a monitoring workflow actually usable. That advice matters, especially for smaller teams. If you do not have much data, it is usually better to respect time, order, than to overfit a monitoring scheme to a tiny sample. That decomposition helps separate different kinds of change in the data generating process. Once you name the parts separately, it becomes easier to think about which kind of adaptation might actually help. That line points to a common strategy. Learn features that stay stable across domains. Stability in representation can make transfer more reliable when the raw data changes. Label shift is one of the cases where you can sometimes adjust the predictions after the fact. The important part is that the class proportions changed, and that can often be handled differently from a change in the features themselves. That claim sounds useful, but it should be treated carefully. Detecting drift is hard enough. Identifying the exact retraining data from monitoring signals is a much stronger statement. An SLA gives a concrete reliability target for the underlying platform. That matters because ML systems depend on infrastructure guarantees, and the model can only be as dependable as the services around it. That is a good example of a metric shaping the behavior it measures. If you optimize only for completion, the system may learn to favor shorter content, even if that is not the broader goal you care about. That title captures a useful engineering principle. If a detector is going to miss something, it is better for the failure to be visible and understandable than to let the problem hide inside the system. That idea reflects the observability mindset. Collect the signals that will help you reason about the system later. You do not want to discover after an incident that the one metric you needed was never captured. At scale, monitoring is not just a modeling issue, it is also a data engineering problem. Huge event volumes require careful pipelines, storage, and processing before the metrics are even available to inspect. That term is stronger than simple logging or dashboarding. The goal is to make the system explainable enough in practice that you can reason about what happened when something changes. Logs are one of the basic ingredients of observability. If you store them well and can search them effectively, they become a way to reconstruct what the system did when a metric starts to look wrong. A live monitoring pipeline often depends on streaming rather than batch computation. That difference matters because alerts and drift signals are only useful if they arrive soon enough to act on. Once you monitor enough signals, the storage and organization of that data become a system in their own right. Scale changes the problem from simply collecting metrics to managing them, so they remain queryable and useful. That idea connects back to the monitoring story, because explanation is part of understanding drift and model change. When a feature matters too much or changes unexpectedly, important signals can help you trace why the model behaves the way it does.